Okay, let's start with the program. We will now switch directly live to our 5G Bavaria testbed to Karin and the Fraunhofer team, and they are waiting for us in the testbed, in the hall, in the link hall.
The 5G Bavaria testbed. So hello to our 5th 5G dialogue. So like Inchi said, we are live in our testbed. This is my colleague Ralf Dubler. But we have today 3 key persons of our 5G initiative on board. The first one is Bernhard Niemann. He is the overall leader of the 5G initiative. We have Thomas von der Grün. He's the project manager of the 5G testbed. And Ralf, he's one of the key persons building up this testbed and running the testbed. And I hope we prepared a very interesting day or interesting hour for you. So we will after 2 short presentations, have a walk through the testbed. We will see the core, we will see the infrastructure, the RAN radio infrastructure. So I think it will become a very interesting part of this 5G dialogue. At the beginning, we like to start with a short survey because we like to understand where you are at the moment. What's your idea about 5G? So Inchi, she will share a short questions regarding the timing of 5G. When you plan to use 5G in your company, or perhaps if you not have your own company, when you plan to dive deeper in 5G. So I hope you all can see that we really have a great part of the participants who are planning to start with 5G 22, 23. And this is really a very good way to start. I will share some slides. So I think as you all not hearing the first time about 5G, we have in the current situation that we have the release 15 available. The release 15, if you look on this magic triangle, is the release who has a main focus on enhanced mobile broadband. But 5G is an ongoing development. So we will see release 16 and release 17 in the next years. And this will handle also massive machine type communication and ultra reliable low latency communication. And also with release 17, we will also have some sustainability features on board, like low power for positioning. This ongoing development and how this ongoing development can be described is also on this feature of 5G positioning. If you look on this slide, we start with the release 15. There's no ambitious requirements, only 20 meter. But with the upcoming releases, we will improve up to 3 meter indoor, up to 1 meter, and up to 20 centimeter for IoT devices. So this is very promising. But nevertheless, this release 15, which is available, is a release which still can handle many use cases which are required from the industry. We have done a research with the German Association of Machine Builders. We have made a deep dive in over 30 use cases. And the interesting result was, and this is on the left side, this release 15 can handle many of the use cases. And there are only small parts which need release 16 or release 17. So it's a really promising time, and that you plan to start in the next 2 years is, I think, the right time, because also then the release 16 will be available. But still, with release 15, you can do many things in your plant. And so it's now, this was a short introduction. So I think the idea of today is let's get 5G started. Not only in a smart factory for connected manufacturing, but also for many other use cases, like in agriculture, for smart cities, industrial automation. So there's also mission critical applications. We have many projects running in this area. So these were only these 4 slides for the introduction. And now it's time that Bernhard will take over and gives you more details about the 5G Bavaria initiative.
Basically, what I would like to do is to give you a brief overview on how the Nuremberg testbed is embedded in the overall 5G Bavaria initiative and other activities within Fraunhofer IIS. First of all, let's have a brief look on how we as a research institute see the development of a new generation of mobile communication standards. So basically everything starts with research. You have to work on challenges, you have to figure out KPIs, you have to work on new functionalities, find solutions for the challenges. So that is the basic research work. Then the next step is standardization. So from all the proposed solutions, companies have to agree upon a set of functionalities that is relevant for the new standard generation and that will be implemented. And of course, they need to agree on these solutions to be adopted. That is an important step in order to ensure worldwide interoperability. And then, of course, the last step is applications. So once deployment has started, equipment is available, the rollout needs to start and new applications can be tested. As a research institute, our ambition is to participate to this complete cycle or all the phases of development of a new communication standard, so really from research to application. And in order to enable that, we have in Erlangen a test center, which is more focused on simulation, proof of concept, demonstration, emulation. And then we have test beds. We have the Testbed Industry 4.0 in Nuremberg, which is the focus for today's event, and we are also in the bring-up phase for an automotive testbed in Rosenheim. So basically today I don't want to talk about the research phase. Research for 5G is more or less over. So as a research institute, we've started to work on 6G. So this is not the focus for today, but I would like to briefly tackle standardization, because also here you see something like a phased approach. So basically, a new communication standard is not really one monolithic thing which suddenly appears and all the functionality is available, but it comes in releases. So there are various releases, and with each release, some new functionality is being added. And as my colleague Karin Leudel already pointed out, especially interesting for industrial applications are the release 16 and 17, which have been finalized in standardization or are expected to be finalized shortly. And with that, I would like to come to an important point, basically a gap between standardization and deployment, because what typically happens is that in standardization, a new release is being finalized, and then there is a gap until equipment is available, until really the new functionalities are in the field. And what we would like to do, where we would like to help as a research institute, is in bridging this gap between standardization and deployment. And as a very early thing, what we offer is simulation or emulation, hardware prototyping, proof of concept, demonstration of certain concepts. And then, of course, what we will focus today is the test beds, and the test beds are basically important to enable early testing of new functionalities to validate applications. And with that, I would like to hand over to my colleague Thomas von der Grün, who will talk more about the application side now.
Thank you, Bernhard. Also a warm welcome from my side from Nuremberg. And I would like to continue on the 5G initiative, which is an important activity in our research and, as Bernhard already pointed out, on our development work for technical solutions, especially with the focus of today for production, for logistics, for smart manufacturing. So on the left side, the test center itself covers or comprises research and development work about industrial IoT communication and positioning, for example, ultra low latency communication, platforms for in the frequency range 1, 3.7 gigahertz, and frequency range 2, the millimeter wave range, including MIMO technologies. So we are doing research work in positioning solutions in different measurement principles, architectures, and accuracies. There is also research work ongoing in artificial intelligence, or being more precise in machine learning and deep learning, also with a focus, for example, on positioning. There is new research work which is focusing on energy savings in these kind of networks. So all together, these technologies are the basis for your smart manufacturing solutions, so for closed loop control, for real-time locating services, for digital twin, for augmented reality solutions, and far more. The testbed in the middle, as of today's focus, gives an early hands-on experience to latest development in 5G for your development and application. You can test 5G to its limits and do this under realistic conditions and environment. So could you please switch to the next slide, Bernhard? So let's see what we have and what we provide. So the key element is the standalone campus network. It's a 5G new radio network and a 5G core. It's an Open RAN based system. Open RAN means that the interfaces between the commercial off-the-shelf available hardware is standardized and can be used. So what we are doing, we are working in communication and positioning technologies. We have the light frequency bands available, as I already explained. And this is an open testbed. This forms an open testbed. And it's a really large testbed. It's 22,000 square meters over 2 sites, one in Erlangen, one in Nuremberg. It covers production or manufacturing sites, offices. It supports the indoor and outdoor transition. It also includes the capabilities of the evaluation of the technology, because that's a testbed. So this is a hands-on experience you can get on how this technology is really behaving and how this really working in a specific environment. And for sure, there are also the keywords like machine learning and edge computing, which are very essential, especially in a Open RAN standalone campus network. So that's a campus network which is limited to our premises, to our 2 sites. And there is no connection to the public network. So could you please switch to the next slide? So what you can see is in the center, the principal layout of our Nuremberg area, at least. There are on the left side some figures about the equipment which is available. If you sum this up, it's around 50 radio units which are deployed and different frequency ranges. There is also the site in Erlangen focusing also on a parking lot and also the lab environment and the office environment. And what's very important, there are also the technologies which are existing as state-of-the-art in the industry already. So Wi-Fi 6, which is a quite new technology, but nevertheless, it's a technology which is widely used. There's ultra-wideband technology, for example, for positioning available. And it's very important to do some benchmarking to better understand the coexistence, the combination. And at the end, it's all about the target to find the most suitable solution for you and your application. So that's a lot about technical equipment and features. And at the end, it's all about the people. And in the team, we have more than 60, 65 committed researchers. We have a broadly diversified know-how from standardization, as you have seen from Bernhard, the 5G technology itself, the overall implementation of the technology, to application. So we are Fraunhofer, so the application is always in our focus. We do the development and testing services. So let's talk about your ideas. This is the format, 5G Dialogue, to get in contact with you. So enjoy the rest of the show.
Yeah, because as you cannot be live here, I think it's, oh, have I shared the right one? Inchi, have I shared the screen? Yes, looks like, perfect. So normally we have the people live here in our testbed and we can really show the infrastructure, the size of it. But there it's a short video. I hope the sharing works. Mm-hmm. So this is the office building, like Thomas described, is a smart cell infrastructure. They are available, and this on the left side is this industrial area, so which we are in today, as you will see it now. So this is the view inside the industrial area. We are on the left side, and this is the view through the hall. So it's over 1,400 square meters, where we can build up use cases, where we can install any infrastructure. And like Thomas said, we have everything available plus 5G now. So this is really a nice infrastructure. And this is also the point where I like to give over to Ralph, who prepared a very nice walk through the testbed. And also the excuse in front, we have the core live. So there will be a background sound there for all the cooling. But it's a great chance to really see how an implementation of an Open RAN core looks like. So Ralph, it's your turn.
Thank you. Okay, with 5G, we have for the first time the situation that that high professional telecommunication technology is not only used by operators, by network operators, but it is going to be spread out in the industry. So we see that even smaller companies have interest in 5G and they have to work with 5G because 5G will become kind of a standard in communication also in the industrial environment. Unfortunately, not every robotics manufacturer is a telecommunication expert. Not unfortunately, that's simply normal. And that's the reason why we in Fraunhofer here, we thought it might be a good idea to build a nice playground, not only for us and our internal researchers, but also for these companies outside that do not have the expertise, that do not have the know-how, but they still have to develop products that work with 5G, that have 5G connectivity inside. And for them, we have built here, as I said, a nice playground, and we invite everybody to come here and work together with us here on their products, on their problems, challenges, with our help together. That's what we can offer here, and that's what we want to offer here in this testbed. So what have we built up? We have built up a 5G standalone, Open RAN based campus, all on-premise, non-public network. What does this mean? 5G standalone. Typically in the commercial networks outside, you have a 5G non-standalone architecture. This means that your UE, your user equipment, is connected to an LTE cell in the idle mode. And as soon as you go active, as soon as you start video streaming or you need high data rates, then you just get a second carrier assigned, and the second carrier is a 5G carrier. So it's a carrier aggregation of the existing 4G connection that you have. A lot of control information still goes on this channel, but the data pipe is the 5G. You stream your video, and once your video is streamed and you close the connection, the 5G carrier is disestablished and you go back to LTE only. in our network, we only have 5G. So we have, as I said, a standalone network. We choose this because this will be industry standard as well. In the industry outside, we will not see non-standalone activities simply because the LTE frequencies are not freely available. And no one wants to handle two technologies if you can do the same with just one technology. Campus. We have a campus net. What does campus mean? Campus means that the German regulator, the Bundesnetzagentur, they have provided a frequency range. This is from 3.7 to 3.8 gigahertz, 100 megahertz bandwidth. And this is open to public use. You just have to apply for the permission to use it at the BNetz A. You just have to pay a really small fee per year. And then you get the permission to use a certain bandwidth out of these 3.7 to 3.8. And for example, we applied for the full 100 megahertz. And that's what we can offer also here in the test hall, in the test bed. Then we have Open RAN. Open RAN basically is a standard that sits above the 3GPP standardization. The 3GPP standard ensures that your user equipment that is developed according to 3GPP will work in every network all over the world. But it does not really describe a detailed system architecture, interfaces, and things like that. This is completely done by the Open RAN standard that sits basically on top of the 3GPP standard. So the Open RAN standard defines a system architecture, it defines interfaces, and it ensures the interchangeability between different components from different vendors. This is something we have never had before in the telecom industry. We always faced proprietary solutions. So we have currently we have a few big manufacturers, and they all have their own solution. You can't just change G node from A with a core from B and connect them and they will work. No, it will not work. With Open RAN, the idea is that the interfaces are open and exactly this scenario shall work. So we have described SA, we have described campus, we have described Open RAN. Now we have isolated on-premise. We do not have any interaction with the outside world. We do not have any interaction with a commercial telecom network that we see here in our test hall. We have everything on site, so we do not even have some logical connection to the outside world. The complete system is inside, installed here, and is running here. I think I explained a bit about the Open RAN system architecture. Basically, the system is divided in two main parts. One is the core part and one is the RAN part. RAN is like a radio access network part. And the core part is basically the brain and the head of the system. In the core, all the central functions are handled, like the user management, SIM card. This is all done in the core, while the RAN basically bridges the gap down to the user, to the interface. The RAN itself, it's split into three components. One is the radio. The radio basically sends and transmits and sends and receives messages. It also measures, so it measures the signal strength of the UEs that are connected. And then it is connected to a so-called digital unit. So the radio itself, it's quite a stupid thing of a stupid piece of hardware. And then it sends all the raw data over to the digital unit. The digital unit then does kind of baseband processing and does first logical processing of the data. The digital unit is then connected to something that's called the centralized unit. Even if it's called centralized, it's basically a decentralized intelligent node. So it takes a lot of the intelligence that the core would normally do. It takes it out of the core and distributes it into the network. So you have a load distribution inside your network, and only the really higher layers are handled by the core system. A typical distribution, for example, is that you take 3 or 4 radios and connect them to one digital unit. Then you take 3 digital units, for example, and connect them to one CU, to one centralized unit. And then you take 3 or 4 centralized units and connect them to one core network. This is also how our setup here is, and I will explain this a bit more in detail. As we have heard from the previous presentation, we don't only have a site here in Nuremberg, we only have a site in Erlangen, and also in Erlangen the test bed is working. It is in principle not intended for public use, so we're not going to rent this out in Erlangen, but for our internal research and development activities, we also have radio nodes in Erlangen. They are connected to the same core that is located here in Nuremberg. So in Erlangen, we have some radio nodes, we have a digital unit, we have a centralized unit, and then we have a dark fiber connection over here to the core. So this core handles the Nuremberg and the Erlangen system completely. The complete architecture of Open RAN is based on virtualization. So each of these functions is completely virtual. It runs on commercial off-the-shelf hardware, but it can be, let's say, shifted around in this network. You can move it. You can even send it up to the cloud. I will explain this in a second. I think we have covered a lot of theory.
Yes.
And let's have a look at the real thing now.
Yes, I think this is what you're all waiting for. So my colleague Tim, he will switch on the camera and you see Ralph walking into the core and describing how our Open RAN core is
getting a bit loud. Excuses for that. So what you see here is a 19-inch rack. And this 19-inch rack basically is the complete system except the radio stations. If you look at, let's say, old school telecommunication networks, such a system would be a lot of huge cabinets filling a big room very easy. And what we have here is one 19-inch rack. And this isn't even full. There's even some spare space left. Let's explain a bit what is inside here. What you see, this is standard server hardware. It's no proprietary stuff. It's Xeon processors. It's of course high power, but standard. On these here, we run the core system. On these two, we run the centralized unit. In Nuremberg and Erlangen, we have one server for the centralized unit there. And these are the digital units. As I have said, the functionality is not bound to the hardware. It's basically Docker containers these functions are running in. You can take the container, move it from here to here, from here to here. No problem at all. Actually, it's not a complete truth. The digital unit cannot be really put away from this hardware because this hardware is extended with FPGA accelerator cards. The FPGA accelerator cards physically in these servers, they are needed because we choose a so-called functional split in the Open RAN specification that says, as I explained earlier, the radio is completely numb. It just sends raw data and it sends a huge amount of raw data. And this raw data is then taken care of by the digital units. To make the life a bit easier, we have these FPGA cards that do a lot of pre-decoding of this data stream before it enters the digital unit. That's the reason why I can't move the DU, the digital unit, to the cloud, for example. All the rest I could easily send up. So now you may ask why we have 6 big servers for this functionality. Very simple. We currently, at a maximum, we use 3 of them. The rest basically is spare because what we also offer here is not only a network, we also offer mobile edge computing capabilities. So a lot of this power, a lot of this computing power is intended for our researchers, but also for maybe customers that come in with interesting ideas, with interesting use cases that need MEC data on site. So they don't send the data that are transmitted with a telecom network, with a 5G network. They don't need to send the data up to their data center, which will increase the latency again. We can have a lot of calculating power in here already. The radios in the test hall are powered centralized from here, and they are connected all with fibers. They are all connected with 10 gigabit fiber links. Downlink traffic, the typical data rate on the interface here is more than 7 gigabits. even if I only have 1 gigabit of user data, as I said, they send a complete uncalculated raw data, the IQ samples, and this is about 7 gigabit. Again, that's the reason why we need these FPGA accelerator cards to make life a bit easier for the DU servers. Here we see an RF cable, but this is not a radio station. This is just a GPS signal that is transferred here into what's called PTP, precision or precise timing protocol. The timing protocol is needed to ensure that all the radios outside are synchronized on a synchronized time base. As we will not only do communication, but also positioning, time synchronization is the key. That's why we choose here a so-called PTP class C. It's a very, very precise time synchronization. And we come down to 10 nanoseconds of time difference between the different radio stations outside. What you see in between here, this is then just a transport network. It's the XHOL. It's the communication between all these servers. And also it's the link over to Erlangen. As I said, the core system here also serves the system in Erlangen. I think we have enough for this rack. Now let's go outside and have a look at one of the radio stations. This is one of our currently used radio stations. In size, they are about a Wi-Fi hotspot. They are quite small. We currently have installed 8 of these units here in the hall. So one may ask, why do they need 8 radio stations to cover the hall? If you only want to communicate, 4 stations would completely cover the entire premise here. No doubt about that. But as I said, we want to do also positioning. And for positioning, the more radios you have, the better. And also the more different the location of them is, the better. That's the reason, excuse me, that's the reason why we decided to put 4 of these stations on ground level. And then we put 4 on the second floor. This gives basically a 3-dimensional distribution of the radios and helps our colleagues for the positioning a lot to work on their algorithms and to prepare the algorithms. In addition, we have here a huge gate. We can open the gate and then we can go to the outside. This also gives us a huge opportunity to have a movement from the outside with, for example, GPS coverage to the inside with no GPS coverage. Yeah, so you can check if your algorithm seamlessly switches from GPS to 5G localization, for example. Yeah. Coming back to the radios, what we have currently, these are quite, let's say, small radio stations. They have 4 MIMO layers, not that much, and they work in FR1. Having said this, 3.7 to 3.8 gigahertz. This is the current setup that we have, but we're not going to stop to, let's say, make this playground even more fun. Yeah? And what we're going to do in the next year is we work on topics like massive MIMO, beamforming, and millimeter wave. These are the features we're going to bring in over the next year. And the Open RAN, let's say, community, it's a bit shaky regarding their time plans and regarding their roadmaps. So they react very quickly on market demands. So we can't really say what will be available, but we are pretty sure that, let's say, today in 1 year, we have all these nice little things running. Millimeter wave, beamforming, and massive MIMO. So having said this, I think it's time for some question and answers. I give back to my colleague.
Ralph is coming back. And just we have the first questions in the chat. So also here, I like to invite you, put your questions in the chat or open your mic. Oh, regarding the time, I have to close the question round, but we will stay in the call for at least 4:30. So it's only that we like to close official this 5G dialogue. This is what we do every time. This is our 5th dialogue. We close in time and then we stay here for further questions. So I will give back to Inchi, and before I want to say thank you to Ralph, to Thomas, to Bernhard. They really done great in preparing it, and Ralph has done 4 tests running through the area, and I think the connection was good, and you really got a nice transmission from our testbed. So back to Inchi and closing words from your side.
Okay, yes, thank you very much, dear Karin, Ralph, Thomas, Bernhard, for this very interesting insights, and to all our guests for your participation, for your questions. And yes, I would say goodbye. Thank you very much and see you soon. Goodbye.